Good afternoon. Thank you, everyone, for attending our virtual Friday lunch discussion with CSIL's Corrigan-Gibbs. Henry will present the design and implementation of SafetyPin, a system for encrypted mobile device backups. Please feel free to send any questions for Henry in the chat to me, and I will ask on your behalf during the presentation, or send them throughout, and we'll have a Q&A briefly at the end of the presentation. So with that, please, Henry, feel free to take it away.
Great. Yeah, thanks so much for the invitation to speak. And yeah, so I'll be presenting today some work with Emma Dotterman, who's a PhD student at UC Berkeley, and Dave Maziers, who's a faculty member at Stanford. And even though this work actually was published a couple of years ago, because of the pandemic, I've spoken about it almost not at all. So I'm actually really excited to tell you about it. And as Matt said, please feel free to send questions during the talk. I'm more than happy to stop and take questions. I'd much rather, make it as interactive as we can on this Zoom format. So the topic of this talk is the following problem. You have a device like an iPad or a phone, and you want to back up your data, say to Google servers, but without Google being able to see your data. And backup is important, obviously, because people lose their devices all the time. And at the same time, security is important. You don't want Google necessarily to be able to look at whatever your encrypted messages and all the data that you have on your device. So before I get into what we've done, I want to talk a little bit about how this works today. And similar systems are implemented in iOS, in Android for Google's backup. Signal has something called secure value recovery, and other platforms do similar things. And the setup is as follows. So there's a data center with a bunch of machines in it. You can think of these as just basically dumb storage. And the data center also has a secure computing device called the hardware security module, which is essentially just a slow and expensive computer that's supposed to be good at keeping secrets secret. So the hardware security module in its brain has a secret key, and everyone in the system has the corresponding public key. So people can encrypt values to this hardware security module that only the HSM itself can decrypt. So with that setup, this is how mobile device backups go today. So you encrypt, the device encrypts the data to be backed up. So I've depicted that with a big cardboard box with a transport key or a data encryption key that's just a symmetric key. And then you encrypt the transport key alongside the user's screen lock pin. So this is the pin that you use to lock and unlock your phone. And that's encrypted under the HSM's public key. And these ciphertexts are stored in the data center. So later on, when the user, say, loses their device and they want to recover their backup on a new device, what they do is they send an encryption of their PIN, so the same PIN that they used during backup, to the data center. The data center gives this encrypted PIN to the hardware security device, and the hardware security device can check that the PIN used during backup and the PIN used during recovery are actually the same PIN. And in addition, the hardware security module enforces some rate limiting policy to make sure that the user hasn't guessed too many pins, right? Because these are 4-digit or 8-digit pins. If you allowed as many pin guesses as the user wanted, then you could actually brute force recover the pin. So the hardware security module, one of the kind of key job that it does is rate limiting these pin guesses. So if everything checks out, the hardware security module decrypts this backup ciphertext, gives the recovery key to the phone, and the phone can decrypt then this big cardboard box worth of photos and videos and whatever else is there. So this is essentially what's going on today. This is a really useful way to do encrypted backups for a couple of reasons. So one is that it protects against the compromise of Google servers if Google's running a data center, because even if the attacker gets into the storage devices, even if the attacker can interact with the HSM is still going to enforce this rate limit on the pin guesses. So it's actually gives pretty nice security properties against data center compromise. And for the user, it's great because all you have to do is remember your pin. You don't have to carry around any encryption keys, which are difficult to store and kind of cumbersome. So those are the benefits. The drawback is that the security of the entire system rests on the security of the secret key that's stored in the brain of the HSM. So if an attacker can get in and extract that secret key using a physical attack, then it can get everybody's data in the data center. So there's a single point of security failure here, which is not a property that we typically like of secure systems. So the goal of, Yeah. So, and I should say, these physical attacks on HSMs are actually not that difficult to pull off if you have enough time and you have enough money. So there's lots and lots of examples of people extracting secrets from hardware security modules. So this is kind of inexpensive, but a feasible attack. So the goal of this talk is to present to you the system called Safety Pin that gives sort of the convenience and the scalability of these pin-based backup systems that we use today, but with much stronger protection against compromise of the constituent hardware devices. So all the goodness with much stronger security. The principle behind Safety Pin is that we're going to move from a world in which we kind of have one of these hardware devices in a data center to a world in which we have many of these hardware devices in the data center, like hundreds or thousands. And to break the security of the system with Safety Pin, the attacker will have to compromise many of these HSMs. So today, if you compromise one HSM, you get millions of users' data. With Safety Pin, the idea is you should be able to compromise a fraction of the HSMs in the system, and still you should get no users' data. So it's a much, much, much more costly attack if you have the system deployed in the way that I'll describe. In addition, we want to make sure that the system actually still scales well. So today, to recover your backup, you actually only have to talk to one HSM. And with Safety Pin, you only need to talk to a handful of HSMs, like tens of HSMs instead of all the HSMs in the data center. So we kind of try to maintain the scalability property because that's important for operating, it kind of Google or Apple scale. So another way to think about the properties that the system is going to provide is that if you increase the number of HSMs in the data center with Safety Pin, the security of the system measured in the number of HSMs the attacker needs to compromise goes up. And in addition, as you increase the number of HSMs, the throughput of the system, so the performance of the system also goes up. So this is kind of the best of both worlds in some sense. And this is all premised on the idea that compromising in more HSMs is more expensive for the attacker. And we kind of think that that's true because the cost of physical attacks that are needed to extract secrets from these hardware devices essentially scales linearly with the number of HSMs. So physically extracting secret keys seems to take a lot of time, and extracting a lot of secret keys will take a lot of time. In addition, physically attacking more HSM seems to increase the risk of exposure. So carting off one HSM from a data center may be possible by one person, but if you want to steal 1,000 HSMs, you're basically taking apart the entire data center. So we're not focused on protecting against software bugs in HSMs, but if you deploy the system with many different HSMs running different software, you can imagine getting some protection there too. Okay, so that's what we're trying to do with the system. If there's any questions on the setup, I'm happy to take them now. Feel free to ping Matt. If not, I'll keep going.
Yeah, I think we're good to keep going, Henry, for now.
Great. Great. So yeah, so in the rest of the talk, I'll present the kind of basic design of the system and then step through a couple of the key technical challenges we needed to solve to make this work. And at the end, talk about performance and how this might work in a real data center. So just to say it again, the security goal here is that an attacker's chance of recovering an honest client's data shouldn't be much better than just guessing the client's PIN, even if we're operating in a very, very strong attack model. So the attacker we're imagining controls the entire data center, adaptively compromises kind of one by one a fraction of the HSMs in the data center after the client backs up. And then we're also going to allow the attacker to compromise all of the HSMs in the data center after recovery is completed. So we're imagining the client does this backup and recover, and later on someone comes along and hijacks the entire data center. So even under that super strong threat model, we want to provide the property that the best attack is essentially to guess the client's PIN, which is always possible. So I'll explain how backup and recovery work in Safety Pin, and then try to give you a sense of why this system provides the type of security that we want it to. So again, the setting is we have these HSMs in the data center. Each HSM has a secret key in its brain and a corresponding public key that everyone knows. And the phone, when it starts this backup process, has the user's PIN, it has the data to be backed up, and it has the list of all the HSM's public keys. And the phone is going to produce some backup ciphertext as before, but now the way the phone constructs it is slightly different. So what the phone does in Safety Pin is sample a random encryption key, so transport encryption key, which it uses to encrypt the data, so the photos and videos and so on. But then it splits this encryption key into secret shares. So it splits it into 40 pieces, such that all 40 pieces are necessary to recover the transport key. So that's this K1 to K40 is breaking the key into 40 pieces. And then the phone selects, samples a set of 40 HSMs by hashing the user's ID and the user's PIN. So the set of 40 HSMs here depends on the secret PIN that only the user knows. And then what the HSM does, or the phone does, sorry, is it encrypts each share of the transport key to each one of these HSMs that it sampled. So there's going to be 40 ciphertexts coming out here, one for each of the 40 HSMs. And along with that, it'll output this data ciphertext that has the encryption of the user's data. There's some details here that actually are important to make sure the system provides the property that we want. They're kind of technical details of what the encryption scheme needs to satisfy, but it's not super important for this talk. Okay, so why is this the right thing to do? So take this data encryption key, split it into 40 pieces, and encrypt one for each of the HSMs, where the set of HSMs is sampled using the user's PIN. So the idea, the kind of intuition behind security is that if the attacker knew which 40 HSMs to compromise, it could actually recover the user's backed up data, because the attacker would just go to the correct 40 HSMs, extract the secrets from those 40, and then recover the user's data. But the trick here is that the attacker doesn't know which HSMs to compromise, because which HSMs the attacker needs to compromise depends on the PIN, which the attacker doesn't know. And what we show, we give a more precise security analysis that shows that essentially the attacker's best strategy is just to guess the PIN. So the attacker really can't do better than guessing the PIN, which it could have done anyways without compromising any HSMs. And essentially, unless the attacker guesses the right PIN or guesses the right HSMs, it learns nothing about. It's not able to decrypt, and it's not able to recover the user's backed up data. So this is a very hand-wavy argument. In the paper, we give a much more precise argument for security. So that's how backup works. A recovery is pretty straightforward. What the phone does is it downloads the ciphertext that it's stored in the data center. It uses the PIN to compute the set of HSMs it needs to talk to for recovery. And then it asks these 40 HSMs to decrypt each of their corresponding key shares, and then it recovers the backed up data. So the phone just has to talk to these 40 HSMs to complete the backup process. There's one sort of subtle limitation that you might be able to notice here, which is since the set of HSMs the user talks to during recovery actually depends on the PIN, the attacker who's monitoring the data center can actually learn information about the phone's PIN during recovery. And we have some discussion in the paper about how to get around this, but the basic idea is after you recover, you should change your PIN. So that the attacker can't basically exploit this information in the future. Okay, there's one other sort of issue with this basic design that I want to mention, which is that we'd like the client to be able to recover their data even if some of the HSMs fail, right? Because there's benign failures in data centers all the time. So today you do this just with replication. The client will usually encrypt its data to 10 different HSMs. And we can do something pretty similar in safety PIN. So we just replace additive secret sharing with something called Shamir secret sharing, if you know what that is. And that's essentially allowing us to split the key into many shares such that as long as not too many HSMs fail, the client can still recover its data. So that's kind of the basic design. If there's any questions, I'm happy to answer them now, or I can keep.
Yeah, we do have one question, Henry.
Great.
What is the reliability of HSMs like? Is it the case that all 40 shares are needed to recover the data?
Great. Yeah, great question. So I hope that this slide gave you a little bit of information about that, but this is all parameterizable. So essentially you can say, okay, I'd like to tolerate the failure of 5 HSMs or 10 HSMs or 20 HSMs. And when the client encrypts, it encrypts its data in such a way that as long as not too many HSMs fail, it can still get its data back. The reliability of HSMs, we actually looked at this, and I'm not going to remember off the top of my head what people do, what say Google and Apple do in terms of rotating keys, but I think we expected, HSMs to last, say, 3 years on average. And if you have thousands of these HSMs in the data center, they're going to turn over, a fair number of HSMs are going to turn over every month, but not so many that you can't handle it with this kind of Shamir secret sharing.
Awesome, thank you.
Great. Any other questions, Matt?
That's it for right now.
Great. Yeah, please keep asking questions. This is like the best part of giving talks. So cool. So let me talk now about sort of 2 technical challenges that we had to solve to make this work that are not addressed in the basic design. So the first one is that as I was stepping through the recovery process, you'll notice that the client actually reveals during recovery which hardware devices it needs to talk to decrypt its backup. So for example, this phone needs the secret of this HSM and this HSM and this HSM to recover its backup. But the problem with that is that an attacker could kind of observe that the client talked to those 3 HSMs, and then after recovery completes, the attacker could go in and extract the keys from those 3 HSMs. And that would kind of allow a pretty low cost attack that would recover the client's backed up data. So to prevent that, our idea is to have, after recovery, each HSM revokes its ability to decrypt the client's ciphertext. So even if the attacker goes in after the fact and compromises these HSMs that the client talked to, the attacker learns basically no useful information that's going to help it decrypt the client's data. There's this idea of being able to kind of revoke the ability to decrypt the ciphertext is known as puncturable encryption and has been around for a while. And I think is a really clever way to provide this kind of post after the fact security.
Henry, we do have a few questions if I could.
Great.
On the limitation of attacker monitoring the recovery process and guessing the PIN based on HSMs being talked to, wouldn't the same limitation be valid for a backup process?
This is a great question. So the key thing about backup is that the client doesn't actually talk to any HSMs during backup. So during backup, all the client does, the client has the list of HSM public keys. The client picks some of these public keys and produces a ciphertext. And that ciphertext gets stored in the data center. So during backup, there's no communication with the HSMs at all. So I hope that answers your question. So basically the same issue the issue only happens in recovery when you need to interact with the HSMs. For backup, you don't actually need to talk to the HSMs at all.
Thank you. And then one more that came in, does the algorithm choose HSMs depend on the number of HSMs?
Yes, it does. Essentially, so what we use this hash function to sample a random subset of all of the HSMs. So in that sense, it depends on how many HSMs you have in the data center. But this algorithm is not terribly sophisticated. It's you use kind of an off-the-shelf cryptographic hash function to generate some random bits, and those random bits used to select a subset of the HSMs.
Great, thank you.
Yep, cool, great questions. So this is the where we are. We're talking about how an HSM can revoke its ability to decrypt a ciphertext using this thing called puncturable encryption. So the way puncturable encryption works at a very, very high level is that the secret key for one of these puncturable encryption schemes or revocable encryption schemes consists of a big array. And it's something like 64 megabytes of data for the parameter settings we need. And then when the HSM wants to revoke its ability to decrypt a particular ciphertext, it just deletes some elements of this secret key, and that prevents the HSM from decrypting that same ciphertext in the future. The schemes for doing this are actually super, super clever and nice, and unfortunately, I don't have time to talk about them, but I highly recommend looking them up if you're interested in this. So this actually works quite well. The problem in our setting is that these hardware devices don't have enough storage to store this big secret key. And so what we decide to do instead is actually have the hardware device outsource the storage of the secret key to the data center, while still kind of making sure that we can protect against future compromise. Because now if the hardware device outsources this array to the data center could be adversarial and might not delete the things that it was supposed to delete. And this would mess up the kind of forward security property that we want. So let me explain how we do this. So we call this forward secure outsource storage. or sometimes it's called forward secure encrypted RAM. And this is an idea that's been around for a long time that we kind of specialize to our use case. So the idea is that the HSM gives to the data center an encrypted kind of tree where each element in this tree is stored as a ciphertext encrypted under the key of its parent. So each of these nodes has a secret encryption key. Think of this as like an AES key, symmetric key. And each key encrypts the ciphertext of its two child nodes. So the root key basically gives you information that allows you to decrypt the entire tree, while a parent, sort of an internal node in this tree, can only decrypt the values of its children. So this is takes a little bit of time to wrap your brain around what's going on here. But what this lets us do is have the HSM only store a single encryption key, and the data center stores this entire encrypted tree. And then when the HSM wants to delete an element, securely delete an element in this tree, what it does is it deletes the element, tells the data center to delete this element, and then the HSM re-encrypts all the nodes on the path to the root with fresh encryption keys. And then the HSM replaces its internally stored root encryption key with a new one. So what happened here is that now if someone compromises the HSM, it can recover all the values in this tree, but it can't recover the deleted values here because the key that was needed to recover that deleted value was stored in the HSM's memory that it actually wiped. So to get this value, you needed SK, and now the HSM is only storing SK prime. So by kind of rotating keys in this way, the HSM can actually securely delete elements of this array, even though the data center is storing the array. So this is how we use this forward secure outsourced storage idea to allow the HSM to outsource the storage of this big secret key array while still letting it delete elements of the array. The other nice thing about this, because we're working with a tree structure, is that each operation on this data structure only requires a logarithmic number of symmetric key crypto operations in the size of the array. So if you did this kind of naively, this outsourcing naively, it would take many, many minutes of computation to update the key. Whereas for this tree-based scheme, as we use it, it's less than a second of computation, even for a very, very slow HSM. So, right. So just to sort of summarize what happened there. So during recovery, the client reveals which HSMs it needed to talk to for backup. And then those HSMs revoke their ability to decrypt that client's data. So this is, and they do that using this forward secure outsourced storage. The one asterisk there that I put just to be completely transparent is that there is kind of one window of compromise where if the attacker can get in and extract the keys before the HSMs have done this key rotation, it could potentially get the user's data. But our thought is that's a very, very difficult attack to pull off because it would require kind of getting into the HSMs at exactly the right moment, and seems, plausible, but difficult. Okay, so that's how we handle this after the fact compromise. If any more questions on this in the chat?
Nothing right now, but everyone feel free to send any questions as you have them to me.
Great. So, okay, so let me talk about another technical challenge, which is how we do the rate limiting of pin guesses. So the whole point of using these HSMs is they limit the number of guesses that anyone can make on a particular user's account. And this is to prevent brute force pin guessing attacks, because if you're only using a 4-digit pin, then you can just, there's no rate limiting. The attacker can just guess 0000, 0001, 0002, and pretty quickly recover the user's data. So rate limiting is super important. But the problem in this distributed system that we've set up in Safety Pin is that there's no single hardware device that has a global view of how many guesses a particular user has made on their pin, right? So no single HSM actually knows how many guesses there's been. So our idea for this was to have the data center actually, which data center might be adversarial, but the data center maintain a log of the user's decryption requests, and then have the HSMs collectively, using a distributed protocol, check the data center's work. So if the data center is doing things correctly, the rate limit will be enforced. If the data center cheats, the HSMs will notice it, and the whole system will essentially grind to a halt. And this is how we try to rate limit the number of guesses that, that a user can make on the pin. So let me just try to explain why distributed rate limiting is important in the setting. So you might think, well, why doesn't each HSM just keep a local guess of how many guesses, the local counter of how many guesses the user has made of the pin? And the reason that that doesn't work is that if you just kept local counters, the user could get way more guesses than they should be able to get. So the reason for that is that each pin guess will cause the user to communicate with a different set of HSMs. So if the HSMs are keeping local counters, then when you make the first guess, these set of HSMs will increment their counter. When you make the second guess, this set of HSMs will increment the counter. When you make the third guess, it's a different set of HSMs. And you'll see that the attacker will get many guesses at the pin before any of these HSMs hits, say, counter value 10. So we have to do distributed rate limiting or else security is essentially broken. So, okay, so what do we do here? So as I mentioned, we use this distributed log to enforce a global pin guess limit. And the way this works in safety pin is we have each of these hardware devices hold essentially the root of a Merkle tree computed over all of the entries of this log. So the log gives sort of for each user how many guesses they made at the pin in the last time period, so every month or something. And when the user wants to begin a recovery operation, the client inserts some information, metadata about its recovery attempt into the log. And then it proves to the HSMs, this recovery attempt is logged, and there haven't been too many guesses on my pin in the last month. So by checking, basically the user proves to the HSM that say, there have been only one recovery attempt on my pin so far, and then the HSM will be convinced relative to this digest and will allow the recovery attempt to proceed. So, right. So that's kind of in steady state, this is what happens. The HSM has a digest of this log, and using a kind of Merkle proof, the client can prove that that there haven't been too many recovery attempts made on its pin. But this is kind of only in steady state. The question is then, how do you update the log, especially if the data center is maintaining the log and the data center might be adversarial? So the way that works is as follows. So the client asks the data center to insert an entry into the log. The data center, when it does this, it actually proves to the HSMs that the insertion was valid. And this requires a couple of Merkle proofs to do, and I'm not going to be able to go into the details, but they're in the paper. So essentially what the HSM does is the data center does is it proves to the HSM, here's the new digest of the log, and every update operation I did is consistent with the rate limiting policy. And then all the HSMs will accept this new digest from the data center, and the recovery operations can proceed after that. The way we have the logs check these proofs actually requires each HSM to only check a fraction of the log updates, and that allows us to scale. So even if the number of HSMs is very large, each HSM is only doing kind of a little bit of the work of this log maintenance. This ends up being actually super tedious to get right. There's a lot of kind of low-level details to make sure that both security and scalability are maintained here, but I'll point you to the paper if you're interested. So that's those are kind of the two interesting technical bits. So how do we protect against after the fact compromise of HSMs, and then how do we make sure that that a user can't make too many guesses at a pin? Any questions on that stuff? I know there's a lot of material there, so I hope I didn't overwhelm anyone.
No, I think it's great. I think yeah, if anyone has any more questions, just please feel free. I think everyone's probably just digesting.
Yeah. Yeah. And I know it's actually during lunchtime, so people may be literally digesting as well. Good. So okay, I'll keep going then, and then I'll stop at the end. So yeah, let me talk now about the experimental evaluation. So we were actually really interested in getting this to work in practice on real HSMs. And one property of HSMs is they're pretty computationally limited devices. I already talked about them being limited in storage space, but they're also limited in computation typically. So to see how this might work in practice, we actually got 100 of these solo key devices, which are super low cost. You can think of them as super low cost HSMs. They run at 80 megahertz. So on one of these solo keys, we could do 7 digital signature verifications a second, which is kind of orders of magnitude less than a laptop. So this is very, very, very limited devices. And we hooked them up to a Linux PC that was simulating kind of the data center, and then used a Pixel 4 for backup and recovery for the benchmarks. And all of the code for this is up on GitHub. So, okay, this is what it looked like in practice. We got a bunch of these. Emma got a bunch of these and hooked them up to a computer in her lab. And we ran all the experiments. These are not simulations. These are actually run on the real HSMs. So the first thing that we can conclude is the end-to-end time for both backup and recovery is pretty modest, even though the HSMs are these super slow devices. So for example, to back up and recover, it takes less than a second essentially for both operations. And you have to remember that backing up actually requires encrypting a huge amount of data, right? All of your photos and videos and other information. So this 1 second of computation is going to be negligible in the scheme of things. So that's backup and recovery. There's other costs in the system. So in particular, each phone has to keep track of the public keys of all the HSMs. And we estimate in a kind of a billion phone deployment that this would be something like a couple of megabytes of keying material every day. So this is annoying, but at least it can happen overnight while the phone is plugged in and on Wi-Fi and so on. We thought we have some ideas about how to reduce the key size using fancier crypto, but we haven't, we actually preferred the simpler system, even though the bandwidth cost was a little bit higher. And then the last thing we did is kind of tried to analytically calculate how much this would cost for a deployment that supports 1 billion phones, because really we're interested in the Google and Apple scale. So our estimate is that the cost of storing the data, say 4 gigabytes of data per user per year, is on the order of hundreds of millions of dollars. And then if you add on top of that the costs imposed by safety pin, which is essentially deploying a fleet of HSMs, this is like a couple percent on top of what you pay for just the data itself. So even if you use kind of industry grade HSMs and you tolerate a constant fraction of the HSMs being compromised, say 5 or 10% of the HSMs being compromised, it's a pretty modest cost increase for an end-to-end deployment, we think. Yeah, so just to sort of start or finish where I started. So today we use HSMs to protect encrypted backups, and you only need to compromise one HSM to break user security. With the safety pin system, we really increase the number of HSMs, but also really increase the security. So the more HSMs you have, the harder it is to pull off these attacks. So I think, zooming out a bit, what was exciting to me or interesting to me about this project is I think we all know that cryptographic hardware can help us build more trustworthy systems. So these HSM-based rate limiting for pin-based backup is a super useful way to get both security and usability for encrypted backup. At the same time, though, I think we should be super, super, super skeptical of using these kind of magic hardware boxes to solve our security problems, because these hardware boxes often fail. There can be implementation bugs, there can be backdoors, there can be physical attacks. There's all sorts of ways in which hardware can be weaker than we would like it to be. And so I think the thing that I would like to kind of leave you with is that we should think about using hardware in a way that gives us the benefits of kind of hardware when things work, while also still protects us against the risks of hardware compromise or hardware failure. So we should not have this secure hardware device being single points of failure in our systems, but we should be able to use them in such a way that we get stronger security even in the event of hardware compromise. And I think that's just a really exciting direction for me for building more trustworthy, more secure systems that are also more usable. So that's where I'd like to leave it. The paper is up on archive and the code is too, and then I'm happy to take any questions that are left. Thanks.
Thank you so much, Henry. This is a really super interesting talk. We did get a few questions that I could ask you. Circling back to the question earlier, circling back for an attacker, how does the 40 HSMs chosen, how are they aware of their part of the key share without being communicated with?
Right. So it's the same way that if you have a public key encryption system, so RSA or one of these standard encryption systems, someone can encrypt the ciphertext to you without you knowing that it's happened. So I can encrypt a ciphertext with your public key, and I can give that ciphertext to Google, and you can decrypt that ciphertext, but you don't even know that that ciphertext exists until Google gives it to you. So it's the same sort of idea that with public key encryption, one side can do the encryption, and the person doing the decryption doesn't have to know that ciphertext even exists until some point later on. Well, that's the same principle essentially. Please ask a follow-up if that's not clear.
In the meantime, I have another question.
Mm-hmm.
Can you talk about using fancier crypto methods you discussed to potentially reduce resource usage mentioned on slide 48?
Oh, wow. Yeah, excellent. So now I know exactly where to go. Right. So, okay. So the issue here is that, let me go back actually. Let's see where this, I showed the picture of the secret key. Yeah, excellent. So for this puncturable encryption scheme, there's actually a bunch of different ways to construct them. And there's a trade-off between the simplicity. The simple schemes have look like this, where the secret key is a big array and the public key is a big array. And fancier schemes where the secret key is still a big array, but the public key is essentially constant size. So the sort of simpler schemes are the ones that we went with because they're more computationally efficient and they're sort of much easier to implement. And those use just standard public key crypto. So RSA or Al-Gamal encryption, sort of standard public key encryption. The fancier schemes that have a much smaller public key use what's called hierarchical identity-based encryption, which requires pairings and bilinear maps, sort of fancier crypto. And the downside of those schemes is that they're much more complicated to implement and much more computationally expensive for both the encryption and decryption operations. But the benefit is that it lets you shrink this huge public key array into essentially a single constant size thing. So that's the fancier crypto system I was alluding to, hierarchical identity-based encryption.
Thank you.
Yep.
Another question that came in, SafetyPin's use of decentralization for added security differs from cybersecurity approaches used in the past. What problems in data security inform this technology design decision?
Ooh, yeah, that's a good question. I mean, I think sort of the thrust of most of my research is about eliminating single points of privacy and security failure in systems. So I think anywhere where you have a system with a single point of privacy or security failure, that's often where the system breaks. And so that's not a new idea. That's been around a long time in crypto, even before crypto, right? So if you think about, if you want to launch the nuclear warheads, typically you need two different people to turn a key, right? That's eliminating a single point of privacy failure by having two different people involved to launch the missile. So in cryptography, I think this goes back to secret sharing, which is this idea of splitting a secret into multiple pieces. And then through multi-party computation, which is computation with mutually distrusting parties. And I think it's continued up to now. So I'd say it's not a new idea, but it's a really important and interesting idea that's actually seen a resurgence because of the kind of increasing importance of security in real computer systems.
Great, thank you.
Yep.
And then another question received, which industries and or spaces do you see SafetyPin having the most impact?
I mean, I would love to see this. Yeah. So I guess originally we were thinking of backup for phones and devices like iPads. I'm sorry if you can hear the dogs barking. I don't know. They must have seen a squirrel or something outside. Yeah, encryption for say Android phone or iOS, and that's already, I mean, massive scale deployment, right? There's just billions of phones out there. So if you can do it better encrypted backup for those devices, it's great. I think it could be used anywhere where you have cryptographic secrets that are supposed to be stored on a user's device and then backed up for that user to recover with a human memorable PIN or passphrase. So for example, if you have secret keys for your servers and you'd like to back them up somewhere and have them be decryptable with the passphrase, this system could help you do that. Basically anywhere where you're backing up sensitive data. And the first thing for us was Android and iOS, but it could really be anything.
That's great, thank you. And thank you everyone for all your great questions. I think that's it for right now. But I know that we will have this talk on our website. So if any members watching this later have questions for Henry, we're happy to link everyone together and get those answered for you. But I want to say thank you so much, Henry, for this presentation today. It was really informative.
Thanks. It was my pleasure. Thanks for hosting, and thanks everyone for showing up.